Hello everyone, and this will be our last lecture in Test 2 material. It has to do with something called implicit differentiation. And what is implicit differentiation? I'm not going to tell you, at least not yet. We're going to go through some preliminary observations, and then I'll get around to what implicit differentiation is. But to start things off, just suppose that y is some function of x. So we'll say that y equals g of x. If that's the case, then y raised to the n power is the same thing as g of x raised to the n power. And we know what happens when we compute the derivative of g of x raised to the n power. This is the derivative of a function raised to a power. So we have the power rule as usual times the derivative of the inner function. And there's no surprises there. But since g of x and y are the same thing, then we should be able to rewrite this equation in terms of y. So let's do that. G of x raised to the n power, since y and g of x are the same thing, then g of x raised to the n power is the same as y raised to the n power. And since y and g of x are the same thing, n g of x to the n minus 1 is exactly the same as n times y to the n minus 1. We just replaced g of x with y, and n and n minus 1 stay the same. Well, what do we do with this thing? This is the derivative of g as a function of x. And what's the derivative of y as a function of x? Isn't that y prime or dy dx? So I'll just replace g prime of x with y prime. So now let me, in the next minute or two, summarize what we just derived here. Recapping, this is what we get. The derivative of y to the n as a function of x is n times y to the n minus 1 times y prime. Or if we want to use the dy dx notation, the derivative of y to the n is n y to the n minus 1 times dy dx. Now, I don't know how this is sitting with you, but when I was a student in calculus, this always bothered my mathematical conscience. It really did. Because I'd look at this and say, well, why does this turn out this way when the derivative of x to the n is just nx to the n minus 1? And it didn't seem right to me. Y is the derivative of y to the n, ny to the n minus 1 times y prime. But the derivative of x to the n is just nx to the n minus 1. Now, what is it that's different about this as compared to this? And I guess that's the big question here. This always bothered me. In my mind, this formula should turn out to look exactly like this formula. Now, probably we have a clue as to why these two formulas are different because of the way that the material was presented to us. And we look at this and we say, well, remember, y isn't just a variable, it's a function of x. So this is a function raised to a power. And we have to use the chain rule. So that's a pretty good answer right there. The derivative of y to the n is the derivative of a function raised to a power. So if that's what you were thinking, you're absolutely right. And consequently, we have to use the chain rule. And the derivative of a function raised to a power using the chain rule, it's the power rule as usual times the derivative of the inner function. So this is a pretty good answer. Y is a function of x. Therefore, the derivative of y to the n is the derivative of a function raised to a power. And consequently, we have to use the chain rule. Power rule as usual times derivative of the inner. Or derivative of the outer, n something to the n minus 1, evaluated at the inner, y, times y prime. So the fact that y is a function of x is why this formula looks the way that it does. And I don't know if anybody ever told me that when I was taking Cal 1. I'm not sure it was explained to me that way. But if they did explain it that way, I don't think I would have been completely satisfied. I still think that I would have had some objection or some question needling me. And I'll tell you what that question would have been. So I guess if I were decades younger and sitting as a student in this class, listening to the older version of me give the lecture, I'd look at this and I'd say, well, I get it. Y is a function of x, so y raised to the n power is a function raised to a power, and we have to use the chain rule. The power rule, as usual, times the derivative of the inner function. And I'd say, I get that. But it seems like the only reason that I know that y is a function of x is because we were given that information right at the beginning of the lecture. We were told, suppose y equals a function of x. We were given this information. So yeah, when I see this, I realize y to the n power is a function raised to a power. But suppose that we hadn't been told that at the beginning. Suppose nobody told us right at the beginning of this lecture that y is a function of x, y equals g of x. Suppose we hadn't been told that. Just looking at this, how are we supposed to know that this is the derivative of a function raised to a power? So let me erase this and just write another question down. You know, I guess this is the $65 million question. We were told at the beginning that y was a function of x. But suppose nobody gave us that information to begin with. I mean, what are we? Are we all psychics or something? How are we supposed to know that, oh, this is the derivative of a function raised to a power? And this, nah, just a variable, x to the n, that's all it is. Do the power rule and that's it. Don't need to use the chain rule. How are we supposed to know which one of these is a function raised to a power, if either one really is? What is it about the appearance of this that identifies it as the derivative of a function raised to a power, and the appearance of this that tips us off that this is just the derivative of a variable x raised to a power? Is there anything that we can home in on, that would tell us, nope, this one's definitely different than that. This is a function raised to a power. This is a variable raised to a power. What is it that identifies this as being a function raised to a power? Do you see anything appearance-wise that's significantly different here than it is here, other than the names of the variables? Here we have x to the n. Here we have y to the n. But appearance-wise, what's different about this compared to this that tips us off that this is the derivative of a function raised to a power? What do you think? Even if you don't know why the difference is significant, what difference is it that you're focusing in on here? And you're probably looking at this and saying, well, this variable right here is different than that variable. I don't know if that's what Dr. Rossi's getting at, but that's the only thing that I can see here that makes this a different form than this thing. And if this is what caught your eye, the fact that this variable and this variable are different, you're right. That's the telltale feature. These variables are different. And the fact that they're different tells us that y isn't just a variable, but it's also a function of x. That's what it tells us. And that's how we know to look at this as being a function raised to a power rather than just a variable raised to a power. So let's write that out. That's worth noting. So here we have it written out. The fact that these variables, x and y, they're different variables. The fact that they're different indicates that not only is y a variable, y is a variable, but it's also a function of x. And therefore, y to the n is a function raised to a power. And the derivative of y to the n as a function of x is the derivative of a function raised to a power. So that's the tip-off. These two variables are different. Not only is y a variable, y is also a function of this variable. And that makes y to the n a function raised to a power. So let's see how well we got this concept. Let me put a bunch of things on the board and let's work our way through them. Okay, let's work through these. And this is the kind of thing we've been looking at for a couple of weeks now. The variables are the same. So we look at x as nothing more than a variable. That's all it is. So there's no need to use the chain rule here. This is just going to be what? Nx to the n minus 1. Just the power rule as we know it, right? Now let's contrast it with this. The variables are different. So not only is y a variable, but it's also a function of x. So this is the derivative of a function raised to a power. What are we going to get? Well, derivative of a function raised to a power, we have to use the chain rule, don't we? So power rule as usual. times derivative of the inner function. Or if we like the dy dx notation, power rule as usual times dy dx, derivative of the inner function. Let's do another example. We look at these two things, they're the same. So how do we view y now? Since these two variables are the same, y is just a variable, nothing more. We don't view this as a function raised to a power. So if this is not a function raised to a power, just a variable raised to a power, what should we get? Just the power rule, right? N, y to the n minus 1. That's it. Now, if you think I'm done with this example, not quite. Let's try this. Yeah. Now, if we really understand what's going on here, this is not a big deal. We look at these two variables, and they're different. So, what do we consider x to be? X is a variable, but it's also a function of y. That makes this a function raised to a power. So we have to use the chain rule. Power rule as usual. And then derivative of the inner, where x equals dx dy. Well, let's not stop here. Let's do a few more. These two things are the same. So what do we consider y to be? Just a variable and nothing more. So this is the derivative of y, or y to the first. We're going to get 1. Now, what about this? They're different. These two variables are different. So what do we consider x to be? X is not just a variable, it's also a function of y. And so we're going to say that this is x prime, or derivative of x as a function of y. Well, let's keep it going. Derivative of y as a function of x. The variables are different. So how do we treat this? Y is a function of x, isn't it? So the derivative of y as a function of x is going to be y prime alias dy dx. Okay, another example. The derivative of x is a function of x. These two guys are the same. So how do we view x? A variable and nothing more, right? And what's the derivative of x? The way we've been computing it for a couple of weeks. Just one? Oh, let's stop. Let's not stop now. Let's keep the ball rolling. Derivative of y cubed. The variables are different. So y is what? Not just a variable, but also a function of x. That makes this the derivative of a function raised to a power. So we have power rule as usual times the derivative of the inner function. Derivative of x cubed with respect to x. X is just what? Just a variable, nothing more. So no chain rule here. It's just 3x squared. And let me take one more step, a giant step for mankind. Or maybe a giant leap for mankind. These variables are the same. So how do we regard x here? Just a variable, nothing more, right? So this is not really a composite function. It's just the sine of x. How do we compute the derivative of the sine of x? Cosine of x? Okay. Now these guys are different. These variables are different. So y is a variable. But it's also what? A function of x. And that makes this a function evaluated at a function. It's a composite function. We have to use the chain rule. And the chain rule says the derivative of the outer, cosine of something, evaluated at the inner, y, times the derivative of the inner. One more. The derivative of cosine of x as a function of x. These variables are the same. So we look at this x as a variable and nothing more than that. So how do we compute the derivative of cosine of the variable x? negative sine of x, right? If that's what you said, you're absolutely right. Okay. The variables are different. So we view y not only as a variable, but also as a function of x. And if y is a function, that means that cosine evaluated at y is a function evaluated at another function. We have to use the chain rule, which means we have the derivative of the outer, negative sine of something, evaluated at the inner, y, times the derivative of the inner, right? So negative sine of y, negative sine evaluated at the inner y, times the derivative of the inner. And we could also write that negative sine of y dy dx. Just two different ways of denoting the same thing. So there are our preliminaries for implicit differentiation. And I guess before I go any further, I will define something that I defined early on in the class, but I didn't dwell on it. But I will define it again because it seems much more relevant now. The verb differentiate means to compute the derivative of. And differentiation is the process of computing a derivative. So differentiation is the process of computing a derivative. To differentiate means to compute the derivative of some function. Okay. This is a lecture on implicit differentiation, and I'm going to get there. We've been laying down the foundation cornerstones of this topic, and we're about to forge ahead. Okay, first thing we're going to do is define the word explicit. An equation of the form y equals some expression in terms of x expresses y explicitly as a function of x. In other words, the relationship between x and y is explicit. And as examples, let's look at these three equations. They're all of the form y equals some expression in terms of x. And the relationship is explicit. For example, when x is 0, y is 1. When x is 1, y is what, 6? And so on and so forth. We know what y is in terms of x. We can evaluate y in terms of x. The relationship between y and x is explicit. Same thing here. y equals some expression in terms of x. And let's see, when x is 0, y is 0. But when x is 1, we have sine of pi over 6, which is 1/2. So when x is 1, y is 1/2. When x is 3, we have, no, I don't want 3, do I? Now let's try 2. When x is 2, we have sine of pi over 3. So when x is 2, y is the sine of pi over 3, which is what? Square root of 3 over 2. So when x is 2, y is square root of 3 over 2. When x is 3, y is the sine of pi over 2, which is 1. So again, if we know what x is, we know what y is. And same thing here. When x is 0, y is 1/5. When x is 3, y is 1/2. The relationship between x and y is explicit. Now let's let me write something here. These equations relate y explicitly as a function of x. So just so that we understand that, these are all examples of equations that relate y explicitly as a function of x. They're all of the form y equals some expression in terms of x. Now, let's contrast that with something a little bit different. Okay, this time we talk about an equation that expresses y implicitly as a function of x. We have an equation, some expression in y and x equals some other expression in y and x. This kind of equation is said to express y implicitly as a function of x. And that is to say, y is implied to be a function of x, though not clearly stated as such. And I guess that makes sense. We have an equation that has both x and y in it, so there's got to be some kind of relationship between them. They're related somehow. But just exactly how they're related, we don't know. So the implication is there. Y is a function of x. They're related somehow, but it's not stated in such a way that we can see clearly what that relationship is. And let's look at some examples. These equations express some sort of relationship between x and y. Now, what are these relationships? Beats me. Let's see. When x is 1, we have y squared plus sine of y equals 1 over 1 plus y squared. There's not a person on earth that could solve that for y. God knows what the answer is, but for us mere mortals, no, we don't. There's not a person on earth that could solve that. Same thing here. Let's try it again. Let's let x equal 1. So we have 3 plus 4y cubed over 1 over y times cosine of 1 over y. What's y equal to? We don't know. X and y are related in each case. They both appear in an equation together. But the exact nature of that relationship is not clearly understood. As a matter of fact, it's not understood any better than, well, they must be related. They're both in the same equation. So these equations express y implicitly as a function of x. Now let me ask another question. Algebraically, do you think I could rewrite this so that I have y on one side and all of my x's on the other? Again, that looks like something that no mere human being could do. Just doesn't look possible. So that we could solve for y and have y equals some expression in terms of x, doesn't really look like we could do that with either one of these things. And that leads us to another truth about equations that express y implicitly as a function of x. And I'm going to write that observation on the board now. Okay, here's an important observation about equations that relate y explicitly as a function of x. It says, in general, equations that relate y implicitly as a function of x cannot be rewritten so as to express y explicitly as a function of x. So, in general, if we have an equation that relates y implicitly as a function of x, we're not going to be able to rewrite it so that y is expressed explicitly as a function of x. Now, this statement is not saying that it can never happen. There are equations that relate y implicitly as a function of x that can be rewritten so as to express y explicitly as a function of x, but that doesn't happen too often. More often than not, if we have an equation that expresses y implicitly as a function of x, we won't be able to write it so that it expresses y explicitly as a function of x. I'm not saying it's always impossible, but most of the time it is. And considering the contents of this statement, what I'm about to write on the board next is going to seem rather mind-blowing, but I'm going to do it anyway. Okay, here's that mind-blowing statement that I told you about. This is our immediate goal. Given an equation that expresses y implicitly as a function of x, compute y prime. Now that seems like a pretty tall order, because given an equation that expresses y implicitly as a function of x, we can't solve for y most of the time, and yet we're supposed to compute the derivative of y? Really? Huh. Well, yep, that's what we're going to be doing. And I'm going to throw out a little bit of terminology here. Okay, here's our terminology. And remember what our immediate goal is. Given an equation that expresses y implicitly as a function of x, compute y prime. Boy, is that a tall order or what? But here's the remark. This process, that is the process of computing y prime, given an equation that expresses y implicitly as a function of x, is called implicit differentiation. Let me say that again now that I've included the y here. The process of computing y prime given an equation that expresses y implicitly as a function of x is called implicit differentiation. And that's the name of what this whole section that we're working on. Implicit differentiation. So that's what we're going to be doing. Given an equation that expresses y implicitly as a function of x, compute y prime. That's what we're going to do. Okay, easy exercise. Just one to get us started. Y is expressed implicitly as a function of x. And maybe we could kind of sort of solve for y in terms of x, but we're not going to, because the object here is to learn how to compute y implicitly, compute y prime implicitly. So that's what we're going to do. Especially since, generally speaking, when we have an equation that expresses y implicitly as a function of x, generally speaking, we won't be able to rewrite it in the form of y equals some expression in terms of x. So we need to develop a technique for computing the derivative of y when y is expressed implicitly as a function of x. So even though we can kind of sort of solve for y here in terms of x, we're not going to do that. This is a simple example. But we're doing it just for the sake of illustration. And I don't know what else to do, but we got to do something, right? So my first inclination, because I don't know what else to do, is just to compute the derivative of both sides of the equation with respect to x. Now, it might work, might not. And let's see, now that we know what the word differentiate means, I can use that. Differentiate both sides with respect to x. Now, if it works, fine. If it doesn't work, it doesn't mean that it was a bad idea. It's a good idea. But if it doesn't work, it just means that this was a good idea that didn't pan out. That's all. So let's see what we get. We have the derivative of a sum, so we can differentiate each term separately. The variables here are the same, so we look at x as just being a variable, nothing more, and the derivative is 2x. Now we move to the next term. The variables are different, which means not only is y a variable, but it's also a function of x. So this is a function raised to a power. So we do the power rule as usual, and this is y to the first. Power rule as usual times the derivative of the inner function y prime. And then we move to the other side. This is the derivative of a constant, right? We get 0. Now, before I start scrambling and trying to figure out what to do next, maybe I need to revisit the exercise and remind myself what it was that I was trying to do in the first place. The instructions say compute dy dx, or compute y prime. And I look at where I am and I go, wait a minute, this is what we want. And you know what? We have it in an equation. All we have to do is solve for a y prime, just like we'd solve for any other variable. That's all we have to do. It's right here in an equation. We just solve for it algebraically. So I guess that's going to be our second step. And in particular, let's see, get all the terms with a factor of y prime on the left and everything else on the right. Okay, this doesn't have a factor of y prime. We got to ship it to the other side. This term does have a factor of y prime. It can stay right where it is. So we have 2y times y prime. Okay. And the second step that we usually do here is pretty much done for us. Usually we factor out y prime, and that would be when we have more than one term on the left side. So y prime is already exhibited as a factor. Now let's see, the third thing we do, I'm going to throw a new word at you. Divide both sides by the cofactor of y prime. Now, what do I mean by cofactor? Well, if two guys are captains of the football team, they're co-captains. If we have two pilots flying an airplane, they are co-pilots. If we have two people conspiring against the government, they are co-conspirators. We have two things multiplied together as factors. They are cofactors. Y prime and 2y are cofactors of one another. So, our last step, divide both sides of the equation by the cofactor of y prime. So that is, we divide both sides by 2y. Well, congratulations, we've just computed a derivative implicitly. And you may look at that and say, Dr. Rossi, you're not quite done yet. And you're right to say that. But actually, I am done. This is y prime, alias dy dx. And I want the derivative of y written as a function of x. But I don't really have that. I have the derivative of y written as a function of both x and y. I don't like that. And when we were doing Leibniz chain rule exercises, we wanted the derivative in terms of one variable, namely whatever this variable was. And here I have the derivative in terms of two variables. I'm not being slipshod. I'm not leaving the exercise half done. There's a reason for me doing what I just did. And I'm going to write that down in the form of a remark. Okay, here's my statement on the matter. Equations, plural, that express y implicitly as a function of x cannot in general be rewritten so as to express y solely in terms of x. So if we have a function that expresses y implicitly as a function of x, usually we can't write it so that we have y over here and solely x is on the other side of the equation. Usually we can't do that. Therefore, the derivative of y computed implicitly cannot in general be expressed solely in terms of x. The bottom line was, given the equation we had, we couldn't express y solely in terms of x. So why should we expect that we can express y prime solely in terms of x? It's usually not going to happen. We don't like it that way. We'd like to have y prime expressed solely in terms of x, but most of the time it's not going to be possible. We don't like it that way, but that's the best that we can do, generally speaking. And that's why I left it like this. Not because I'm the kind of guy that walks out of the house and leaves the front door open. I just couldn't do any better than this. And in general, we can't. That's why I left it this way. Now, let's see if we can take a look at the exercise that we just did and somehow show the validity of our result. Okay, we're back, and we're going to confirm the result of the preceding exercise graphically. Here was the equation that expressed y implicitly as a function of x. This is the derivative that we computed. And notice something about the equation that expressed y implicitly as a function of x. Do we recognize this? This is a circle of radius 1 centered at the origin. So this is the equation of the unit circle, which I've drawn right here. And let me just write a few key points down here. This is x equal 1, y equals 0. And this is y equal 1, x equals 0. And let's see, 45-degree angle right here. This is x equals square root of 2, y equals square root of 2. Let's just concentrate on those points. And remember what the derivative is. We haven't talked about this in probably more than a week. But remember the problem, the goal that we had put before us that started the entire study of derivatives. Remember what it was we were looking for when we started derivatives? Given any function f of x and any point on the graph of f of x, compute the slope of the line tangent to the graph at that point. The slope of that tangent, drum roll please, the slope of that tangent is the derivative. So, let's draw the tangent right here at this point, x equal 1, y equals 0. There's the tangent. And the slope of the tangent is y prime, which in our exercise we computed to be negative x over y. X is 1, y is 0. So that's negative 1 over 0. What's negative 1 over 0? It's undefined, right? Now let me ask you something. What kind of a line has undefined slope? A vertical line, right? So this is right on the money. The slope of the tangent is undefined. It's a vertical line. Okay, let's draw another tangent. Right here. Here's another tangent. And the slope is y prime, which is negative x over y. Well, x is 0, y is 1. The slope is 0. What kind of a line has a slope of 0, huh? A horizontal line, which is exactly what this tangent is. So we're batting 1,000, 2 for 2. Let's do this line last, this point last. I'm going to draw the tangent. The slope is y prime, negative x over y. And here x and y are both square root of 2 over 2. So negative square root of 2 over 2 over square root of 2 over 2, negative 1. Well, let's see. The slope is negative. The slope is negative 1. It's negative, so it's going downhill. But it also makes a 45-degree angle with the x-axis. Slope of negative 1. So this tangent has a slope of negative 1. The derivative that we computed, y prime equals negative x over y, pick any point on this circle, plug in the coordinates, and this will give us the slope of that tangent. So this confirms our result graphically. Now I need to do one or two more examples. This example was kind of an easy one. We need to do at least one more. At least one more. Okay, here's a good example. And there's a bit of a booby trap there somewhere. Let's see if we can pick it out, okay? Now, the first thing I'm going to do to find y prime is what? Differentiate both sides with respect to x. That's right. Looking good. Now on the left, we just have the derivative of a sum. So we differentiate each term separately and just add the results. The variables are the same here, so we just view x as a variable. The derivative is 3x squared. Then we move on to this term. The variables are different, so we view y as a function of x. This is a function raised to a power, so we have to use the chain rule. So we have the power rule as usual times the derivative of the inner function. And now we'll move across to the other side of the equation. It's a sum, so we compute the derivatives of each term separately. The derivative of 5, it's a constant, right? So 0. And then the derivative of x squared y cubed. Anybody smell a rat here? Remember, I did say there was a booby trap, right? It's right here. What do I have to remember? And if you're saying this is a product, so we have to use the product rule, then you're absolutely right. Just because we're learning new rules doesn't mean we can forget the old ones. This is a product, so when we compute the derivative, we have to use the product rule. So I'll say that this is the first and this is the second. And I'm going to get first prime times the second plus second prime. Oh, the variables are different, so this is a function raised to a power. Second prime, so that's power rule as usual, times the derivative of the inner function, y prime. So let's see, I got first prime times second plus second prime times the first. So that's times x squared. And before I do anything else, let me just simplify this. 3x squared plus 4y cubed y prime. And over here, 2xy cubed. And let me move that x squared right here. 3x squared, y prime. Did I do that right? Yep, I think I'm good. Okay. So I have simplified things a bit. And y prime. We have what we're looking for as factors in two of the terms of the equation. So what do? Solve for it algebraically. And the first thing we do is we get all the y prime terms on the left and everything else on the right. This term has a factor of y prime, so it can stay. This term has a factor of y prime. We've got to move it over to the left. This term has no factor of y prime, so it can stay right where it is on the right side. And this term has no factor of y prime. We've got to move it over to the right. Okay, take a look and make sure everything's where it's supposed to be. This guy, we move to the right. This guy stays right where it is. This guy stays on the right. This guy has a factor of y prime. We have to move it to the left. I think we're good. Second thing, factor out y prime. Both terms on the left have a factor of y prime. We will remove that factor. Like this, let's see, 4y cubed minus 3x squared y prime. Yep, that looks good. Equals 2xy cubed minus 3x. And then finally, what was that last step? Divide both sides by the cofactor of y prime. So here's the cofactor of y prime. We have to divide both sides by that. So we have y prime equals this junk. Yep. And I will encapsulate it. This is my answer. Excellent. There's a booby trap in that exercise. Remember what it was. And I want to do one more exercise with a little bit of a booby trap in it. Yep, there are a few interesting features in this one. By the way, in the previous example, notice that we used the same sequence of steps that we used in the first example. Generally speaking, we do. Now, I simplified things after the first step, but generally speaking, when we do an implicit differentiation exercise, we use the same sequence of steps. And hopefully I'll remember to comment further on that after this exercise. Compute y prime, first thing, differentiate both sides with respect to x. So, differentiate the left side and differentiate the right side. And the left side is just a sum or difference, so we'll differentiate each term separately and then just put it together. These variables are the same, so we just look at x as a variable. Derivative of x to the fifth is 5x to the fourth. Now, this thing, we're not going to fall for the same trap twice, are we? It's a product. We have to use the product rule. So first prime times the second plus second prime. And here the variables are different. So we treat y as a function. This is a function raised to a power. So second prime, power rule as usual, times the derivative of the inner y prime. So first prime times second plus second prime times the first. And I feel pretty good about myself because I remembered to do the product rule. But I'm this far from stepping on a landmine. There's something here I have to take care of. Do you see what it is? We have the derivative of the difference of two functions. So we compute the derivative of the first minus the derivative of the second. Well, this whole thing is the derivative of the second, isn't it? But the way I have it written, we're only subtracting this term. I need to subtract the entire derivative of this term. I need to subtract this whole thing. So what is it I'm missing? Parentheses around the whole thing. There you go. Ah, that was a close one. Almost stepped on a landmine. But live and learn, right? This is something that anybody could have missed. So we needed to see this kind of an exercise so that we can be on the alert not to make this mistake ourselves. Now we go to the other side of the equation. These two variables are different, so we treat y not just as a variable, but as a function of x. So sine of y is a function evaluated at a function. We got to use the chain rule. Derivative of the outer, cosine of something, evaluated at the inner, y, times the derivative of the inner with respect to x, so that's y prime. Boy, this is a complicated little devil, isn't it? Now again, I think I'm just going to simplify a little bit. So minus 3x squared y to the fourth. Oops. And I think I'm going to distribute this minus sign to both terms here. So minus, I'll say 4x cubed, y cubed, y prime. Did I get everything? 4x cubed, y prime. Yep, I'm good. Equals cosine of y times y prime. Excellent, excellent. So I've simplified. And now step 2, solve for y prime algebraically. And the first step, get y prime terms on the left, all other terms on the right. Cool. Okay. This is a y prime term. It can stay on the left. This is a y prime term. We have to move it to the left. This has no factor of y prime. We've got to move it to the right. So subtract 5x to the fourth. This has no factor of y prime. We've got to move it to the right. So add this term to both sides. 3x squared plus y to the fourth. And let's say this term goes over here, this term goes over here, this term stays, this term goes over here. I think we're good. I think we're good. You know what? I got a lot of minus signs here. I don't have to do what I'm about to do, but I don't like all these minus signs here, so I'm going to multiply both sides by -1. Okay. Yes, now I have a much more positive outlook. Next step, what is it? Factor out the y prime, right? Oh, did I do that right? I believe I did. And then finally, divide both sides by the cofactor of y prime. And this is the cofactor of y prime. So that will give me y prime equals 5x to the fourth minus 3xy to the fourth all over You know what? Did I miss an exponent here? I'm betting this should be an x squared. If it is, make that correction. I don't have the work beforehand. I erased it, but I'm thinking this should probably be 3x squared, 3x squared. If it is, just make that correction, please. And divide both sides by the cofactor. Voila. Continuing on with this, I'm looking at this, and it seems almost certain that this should be x squared here. I suspect the original term was probably x cubed y to the fourth. And when we did the product rule, we got derivative of the first, 3x squared, times the second, y to the fourth, plus derivative of the second, which would have been 4y cubed y prime times x cubed. So somewhere along the way I didn't copy this correctly. That should be x squared. So if you're watching this at home and saying, wait a minute, where did the 2 go? Apparently when I copied this from one line to the next, I left the 2 off. This looks definitely like it should be x squared here. So if you're taking notes, or if you were grieved by the fact that somehow 3x squared y to the fourth became 3x y to the fourth, when I copied it over probably from this line to this line, I left off the exponent. But this is our derivative. And I guess the lesson that we needed to learn then was that if we're subtracting a term where we have to use the product rule, put the entire derivative in parentheses. That was the big booby trap there. So watch this video again and watch what the booby trap is, or at least go back about 10 or 15 minutes and look for the booby trap, just so that we'll be alert for it when we do exercises like this. And I did say that I would make a comment about something, so I will write that down now. Okay, here's the remark. When we're differentiating implicitly, we typically follow the same sequence of steps each time. The first step, we differentiate both sides with respect to x. And then before we go to step 2, we simplify. Step 2, we solve algebraically for y prime. And that means, first of all, we get the y prime terms on the left and the other terms on the right. And then we factor out y prime. And then finally, we divide by the cofactor of y prime. When we differentiate implicitly, typically we follow that exact sequence of steps every time.